All right, let's jump right in. Welcome back to another explainer. Today, we're going to break down one of the absolute most complex megastructures ever engineered by human hands. We're talking about the offshore drilling rig. This is a total marvel of modern engineering that has to isolate multiple geological formations at vastly different pressures, support just enormous physical loads, and do all of this in some of the absolute harshest environments on the planet. So let's dive into this. A drilling rig isn't just some static tower sitting out there on the water. It's honestly more like a living, breathing, mechanical giant. When you're looking at one of these offshore rigs, you really have to realize that there are thousands of individual components, multiple interacting systems, and operations that literally have to be coordinated with military precision. So today, we're going to demystify this giant by just stripping it right down to its core anatomy. To make sense of all this, we're going to use this blueprint to break the machine down into 4 digestible, highly functional systems: the derrick and lifting, the top drive engine, the mud lifeblood, and finally, the mud returns filter. Starting off with Section 1, the derrick and lifting. You can think of this system as the structural framework and the heavy lifting muscle of our mechanical giant. Now, looking at the primary lifting components, way up at the very top, you have the crown block, which is a fixed sheave assembly. Connected to it by multiple wire rope lines is the traveling block, which, as the name implies, moves up and down. An incredibly powerful motor called the drawworks reels those heavy wire ropes in or pays them out, raising and lowering that traveling block right over the hole. It's essentially a massive, highly synchronized pulley system. And all of those blocks and ropes, they're housed within the derrick itself. Just to ground us in reality here, this isn't just a small piece of scaffolding. The derrick is a prominent steel lattice tower, standing about 50 meters or 165 feet tall. It sits right above the drill floor, providing the immense structural framework required to support everything hanging below it. So why exactly does it need to be so massive? Well, it's because of the sheer scale of the weight it's holding. The drill string, which is made up of individual pipe joints all screwed together, hangs from that traveling block. A typical 5,000-meter drill string suspended from the hook can weigh anywhere between 150 to 200 tons. That is literally the equivalent weight of a blue whale just dangling by a steel thread, spitting deep into the earth. It's wild to think about. As the hole gets deeper, the crew has to constantly add more pipe to the drill string in a process they call making a connection. Think of it kind of like a chimney sweep, increasing the length of his brush as he pushes it further up a chimney. First, the entire 200-ton weight of the drill string is suspended in the drill floor using heavy wedges called slips. Second, the lifting mechanism disconnects and hoists a new section of pipe. And finally, they couple that new 30-foot joint to the existing string, pull the slips out, and resume drilling. It's a highly choreographed routine. You have the crew, known as roughnecks, working in complete tandem with these mechanical giants. Sometimes they're making a connection, and other times they're doing what's called tripping out. That's the grueling process of pulling the entire drill string out of the hole just to change a worn-out drill bit. They use elevators to hoist stands of pipe up to the monkey man, who's waiting high up on the fingerboard, methodically breaking the string apart section by section. That single operation can take up to 16 hours. Section 2, the top drive engine. We've seen the muscle that lifts the drill string, so now let's shift our focus to the motor, the mechanism that actually turns the drill bit and cuts through the solid rock. Historically, older rigs used a rotary table located right down on the drill floor to spin the pipe, but the bottleneck there was that you could only drill 30 feet at a time before having to stop and add another pipe. Modern rigs use a massive evolutionary leap in efficiency, the top drive. The top drive actually allows the crew to drill 90 feet of hole before stopping for a connection. Drilling 3 times as much rock before pausing? That is a real game changer in terms of saving time and money. Instead of a spinning table on the floor, the top drive is a massive electrically or hydraulically powered motor, literally suspended in the air right from the traveling block. It connects directly to the top of the drill string and imparts rotary motion straight down the pipe. It's incredibly powerful, highly efficient, and it is absolutely the industry standard for offshore drilling today. Moving right along to Section 3, the mud lifeblood. We've got the structural skeleton, and we've got the spinning motor. But honestly, no living giant can survive without its circulatory system. So let's transition from the mechanical hardware over to the fluid dynamics of the rig. Our source material really hits the nail on the head here. Drilling fluid, or mud, as it is universally referred to, is the lifeblood of the drilling operation. It's the perfect anatomical metaphor. You have to remember, this isn't just dirty water. This is a highly sophisticated engineered fluid made of clay, water or oil, and heavy minerals like barium sulfate. This fluid is actually performing four absolutely critical jobs simultaneously. First, hydrostatic pressure control. The physical weight of the mud column holds back the high-pressure formation fluids from entering the wellbore. Second, cuttings transport. The fluid velocity flushes the broken rock chippings from the bit back to the surface. Third, high-velocity mud jets cool and lubricate the rapidly spinning drill bit. And fourth, borehole stability. The mud pressure supports the borehole wall, and its chemistry prevents the whole thing from collapsing inward. Because it's doing all of that, the drilling engineer is constantly performing this delicate balancing act with the mud weight, which is usually expressed in pounds per gallon, or specific gravity. In standard overbalance drilling, the mud has to be heavy enough to act as a safety barrier against the explosive high pressures of the formation. If it's too light, formation fluids violently rush in and you lose well control, a blowout. But if the mud is too heavy, the immense pressure fractures the rock, and your fluid is lost into the formation in a lost circulation event. It requires constant monitoring and adjustment. Once the mud has stabilized the hole, permanent support is added using steel pipes called casing. This sets up a fascinating process where the casing acts exactly like a giant syringe. As drilling mud pressure is applied from above, it pushes a column of liquid cement slowly down the inside of the casing, out the bottom, and then up the sides to seal the well against the rock. The mud literally drives the permanent structural integrity of the wellbore into place. Which brings us to our final system, Section 4, the mud returns filter. Let's look at how this vital lifeblood returns to the surface, bringing all the secrets of the deep earth right along with it. This is what completes the circulatory loop. High-pressure pumps push the clean mud down the center of the spinning drill string. It jets out of the drill bit, grabs those rock cuttings, and flows all the way back up the outside of the pipe in the annulus. At the surface, it exits over the bell nipple and is directed right across the shale shakers. These are basically violently vibrating screens that physically sieve out the drill cuttings so the cleaned fluid can return to the active mud pits to be pumped right back down again. Now, those captured rock cuttings don't just get tossed. They are the only physical evidence of what is happening thousands of meters below. A specialist known as a mud logger acts kind of like a geological detective. They continuously examine these rock fragments under ultraviolet light because oil naturally fluoresces, and they measure invisible gas levels in the returning mud. They're tracking all these drilling parameters to build a continuous, real-time geological picture of what the drill bit is encountering in the unseen depths. And this brings us to the ultimate stakes of this mechanical giant. The entire operation relies on the hydrostatic pressure of that mud as its primary safety barrier. As we've seen from catastrophic negative pressure test failures in the past, misinterpreting the pressure data can lead to disastrous blowouts. So it really leaves you wondering, if a multi-million-dollar megastructure relies so heavily on fluid balance, what happens to the rig the exact moment human calculation fails the pressure test? Think on that complex balance of mechanics, fluids, and raw earth pressures. Thank you for joining me on this explainer, and keep learning.